So next is question number 25 and 26. An AM signal 10 1 plus 0.8 cos 2 pi 5000 t and cos 2 pi 10 raised to power 6 t is passed through a tune circuit. The resultant signal is passed through a channel. The gain of the tune circuit is 1 megahertz. At 1 megahertz is 0.8 and at 1 megahertz plus 5 kilohertz it is 0.5. The modulation index of the AM signal at the output of tune circuit and the transmitted power at the output of tune circuit. ठीक है, तो हमको यहाँ पे ये दिया हुआ है, ये एक्सप्रेशन किसके सिमिलर है, ठीक है, आपको दिख रहा है ये किसके सिमिलर है, यहाँ पे हमारे पास साइन वेव है ना, तो ये दिस इज द एक्सप्रेशन ऑफ AM सिग्नल. सो दिस AM सिग्नल फॉर साइनसॉइडल मॉड्यूलेटिंग सिग्नल एंड the expression of sinusoidal modulating signal, the expression of AM for sinusoidal modulating signal in the standard form, it is S of t equal to AC 1 plus MA cos omega MT cos omega CT. This is the expression. So if we compare this, we get the carrier amplitude, we get the modulation index, we get the message signal frequency and we get the carrier frequency. So if we compare, we get AC equal to 10, we get modulation index is 0.8, we get message signal frequency as 5 kilohertz and carrier frequency as 1000 kilohertz or 1 megahertz. Okay, so what about the tune circuit? So the tune circuit is nothing but a band pass filter, practical band pass filter, because if the band pass filter is having variable gain, that means it is a practical band pass filter. So practical band pass filter which is having gain the gain is 0.8 for 1 megahertz. So at 1 megahertz the gain is 0.8 and at 1 megahertz plus 5 kilohertz the gain is 0.5. It means at FC plus FM the gain is 0.5, at FC the gain is 0.8. The gain, the band pass filter, the practical band pass filter we can draw like this. This is a practical band pass filter or the response of tune circuit, because the ideal filter is like this now. This is the ideal band pass filter. So we are saying the practical band pass filter because the gain is constant in case of ideal, but here it is the practical band pass filter, so the gain is continuously changing. So the gain is changing, that's why the filter is like this. The red color is the practical filter response, and or you can say the filter response according to this question. So at FC, that means at 1 megahertz or 1000 kilohertz. So this axis is in kilohertz. The gain is 0.8. This is the response of filter I am drawing, and 0.5 at 1005. At 1005 because 1 megahertz plus 5. So 1 megahertz matlab 1000 plus 5, 1000 plus 5, 1005, and the axis in kilohertz. This is 0.5. So it means that because the filter is symmetrical about the center frequency, whatever will be the center frequency, the filter is symmetrical. So if the filter is symmetrical, so here we will have another frequency for which we will get the same gain, which is 995, because 5 we have to subtract it to make it symmetrical. The same response we will get in the negative side also. And this is the response of this tune circuit. Now we are saying that this amplitude modulated signal is passed through this filter. So first of all we have to see that what are the frequency component present in this, so that we can say that the filter which is ranging from 995 to 1005 frequency component that it will pass. okay, because from here we can see that the frequency ranging from 995 and 1005 can pass through this filter. So first of all we have to see what are the frequency component present in this AM signal. So what will be the response of this AM signal? Because this is AM signal and this is a standard form of AM signal, that means it will have carrier component and two sidebands. So carrier component and two sidebands, and the message signals are sinusoidal in nature, that's why we will get impulse at this frequency. So this is the response of as a filter AM signal, frequency response we have to draw, or you can say the Fourier transform, and the Fourier transform would be, if I multiply it with this, or you can say from here it is AC cos omega Ct. So we will get two impulse at plus minus Fc corresponding to frequency, carrier frequency minus Fc, and this amplitude would be AC by 2, because this is the carrier component and we are drawing the two-sided spectrum because we are drawing the positive spectrum and negative spectrum both. Now if I multiply these two, we get Fc plus Fm, and cos Fc plus Fm, that means we get again two impulse at plus minus Fc plus Fm, and its amplitude is AC Ma divided by 4, because 2 cos A cos B, and again because of the Fourier transform we get half of the amplitude. Let us write once AC cos omega Ct plus AC Ma by 2 cos omega C plus omega Mt, and AC Ma by 2 cos omega C minus omega Mt. The carrier amplitude was AC and now it is half of the carrier amplitude. The signal is having amplitude AC Ma by 2 and its frequency is Fc plus Fm. So we will get the impulse at Fc plus Fm, and its amplitude would be AC Ma by 4, because half of this amplitude, the amplitude is AC Ma by 2, half of this amplitude, and same we will get in the negative side also. So we get minus Fc minus Fm, and we get lower side band minus Fc plus Fm, and this is lower side band Fc minus Fm, and they are also having same amplitude. This is having a frequency Fc minus Fm, and another is mirror image of it. So this is our carrier term, upper sideband and lower sideband, because this is an AM signal. So this is an AM signal, they have two sidebands and carrier. Now this amplitude modulated signal is passed through this filter. Whenever we pass the signal through a filter, suppose this is filter or any system, and it is having response h of f, and input is s of t, and let us say the output is y of t, then we get y of t equal to s of t convolve with h of t, and in case of Fourier transform s of f multiplied with h of f. It means that these two spectrum is going to be multiplied. So s of f and h of f we will multiply. So if we multiply this two spectrum, it is having frequency, it is having component at Fc, and in between Fc to Fm it is 0, Fc to Fc plus Fm it is 0. So if we multiply these two spectrum, we are having spectrum at Fc, and we are having the value at Fc is 0.8, because Fc is nothing but 1000 and Fc plus Fm is 1005 and it is 995. So if we multiply these two, we get a spectrum at Fc, but its amplitude is reduced now. So we get the same spectrum in case of shape, but we get reduced amplitude. So let us say the new amplitude is AC dash divided by 2 and we get at 1000. Now we get at 1005 because now it is having component at 1005 which is having amplitude AC MA by 4 and now it is having amplitude 0.5. So it is multiplied with 0.5 and we get new carrier amplitude, new modulation index divided by 4 and same here at 995 and similarly here also we get same spectrum because mirror image of it minus 1000, minus 995 and minus 1005. This is the output spectrum Y of f, filter output spectrum Y of f. Now previously what was the amplitude? So AC by 2, what is the amplitude of AC by 2? AC is 10, so this is 10 by 2 that is equal to 5 and AC MA by 2, so AC MA by 2, AC into MA is 8 divided by 4, AC MA by 4 it is, so 8 divided by 4 that means it is 2. So the amplitude here is 5, the amplitude here is 2. So this 5 is multiplied with 0.8, here the value is 0.8. So 5 is multiplied with 0.8 that means we get amplitude here at the value is amplitude of is 4. The value of amplitude is at 1000 that is equal to 4 and at this point at 1005 we are going to multiply this amplitude 2 volt with 0.5. So 2 into 0.5 that is equal to 1. So here the amplitude is 1. So on comparing we get AC dash by 2 equal to 4 which will give me AC dash new carrier amplitude as 8. We get AC MA dash divided by 4 equal to 1 which will give me MA dash equal to 4 by AC dash which is 4 by 8 and it is 0.5. So we have calculated the new modulation index which was our first question. So in answer of question number 25 is 0.5. That is option B. Now question number 26. In question number 26 we have to calculate the transmitted power at the output of filter. So the transmitted power is PC 1 plus MA dash square divided by 2 and PC dash we can write because the carrier amplitude has been changed. Now carrier amplitude is AC dash, so we will write AC square by 2, AC dash square divided by 2 and 1 plus MA dash square divided by 2. AC dash is 8, so we get 8 square divided by 2, 1 plus 0.5 whole square divided by 2. So after solving this we will get 32 and this is 1 plus 1 by 4, 1 by 8. So this is 36 watt because this is 9 by 8 and 8 into 4 32. So 4 into 9 this is 36 watt, hence the correct answer is option C. So for question number 26 the answer is option C. Next is question number 27. So a message signal given by MT equal to 1 by 2 cos omega 1t minus 1 by 2 sin omega 2t is amplitude modulated with a carrier of frequency omega c to generate S of t 1 plus mt cos omega ct. What is the power efficiency achieved by this modulation scheme? Because this is a message signal which is amplitude modulated, and because it is amplitude modulated, the expression of standard amplitude modulated signal is AC 1 plus kmt cos omega ct. And on comparing these two, we get k equal to 1. And because the message signal is a multi-tone signal, so we can write this message signal MT as 1 by 2 cos omega 1t plus 1 by 2 cos omega 2t plus 90 degree. So there are two frequency component, one is omega 1, another is omega 2, and when the message signal is having more than one frequency component, we call it as multi-tone modulating signal. And in case of multi-tone modulating signal, the power efficiency or the transmission efficiency is given by MA total square divided by 2 plus MA total square, because message signals are sinusoidal. Since the message signals are sinusoidal, efficiency is MA total square upon 2 plus MA total square. That means we have to find total modulation index, and because there are two frequency component, so there are two frequency component, that's why we will calculate MA total square is equal to MA1 square plus MA2 square. And what will be the value of MA1 and MA2? So MA1 is K into maximum value of MT, which is first component 1 by 2 cos omega 1t, so 1 into 1 by 2, and similarly MA2 is also K into maximum value of MT, which is 1 by 2 cos omega 2t plus 90 degree, and it is also 1 by 2. So the modulation index is 1 by 2 in both the case. So the overall modulation index MA total square is 1 by 2 whole square plus 1 by 2 whole square. That means we get 1 by 2 only. That means we are getting MA equal to 0.707. Now next is transmission efficiency or power efficiency. So power efficiency, we have formula, that is 0.707 whole square divided by 2 plus 0.707 whole square into 100 if we want to calculate in percentage. And for 0.707 we have already calculated, and this value is equal to 20%. We have calculated the three values. For 0.5 it is 11.11, for 0.707 it is 20%, and for MA equal to 1 it is 33.3%. So the 20% eta the power efficiency, and according to the option, the correct option is option C. So if there is a multi-tone signal, even if there is negative sign, we have to consider only the maximum value of MT, because sinusoidal signal is having maximum amplitude either plus 1 by 2 or minus 1 by 2, and we have to consider only the maximum value of message signal. So that's why we have considered this maximum amplitude 1 by 2, and we get the efficiency as 20% according to this modulation index.